Okay, hear me out. With normal small atoms, we know that there is a bounding box for the amount of electrons distance from the core. Once you get into a bigger and bigger structure, eventually that core becomes so powerful and strong that it doesn't have only the most inner core. If you could perceive it as the same as, say, a carbon atom, which most people would never consider the inside of an atom to be the same as having the idea of what would happen if it was another atom just on top of another atom, right? But what if you did think in that way? My mind says that the size of the radius of electrons around smaller atoms could be that they are held in that orbit relative to the strongest amount of just the basic amount of pull that you have with even carbon. So you have 8 electrons around that tight area. Now imagine you have an atom many times bigger than that. And so I'm getting to the planet part in a second. Then you imagine that you have a planet that's a, an atom much bigger than that. And what happens is the orbitals of the regular, what can be around the atom, once they get up to a certain size of proton-neutron pairs, the positive, all of the positive forces aren't just being felt from the outer edge protons, but everything in the atom. So essentially, you have the attractive force of everything that's on the outside, and you could calculate that separately. But what if you also count the attractive forces, specifically the intense attractive forces on the inside of an atom? Well, then, it stands to reason that at a certain magnitude of size, they no longer can just orbit on the outside, but they are pulled in, and that's why you end up with radioactive isotopes like that. That's a silly idea. Whoever thought about atoms like that? Now let's go to planets. I'm watching a video talking about Jupiter possibly being a black hole. That's where this starts. That's where I started my thought process. This idea. Is that the truth? I don't know, but we're gonna have to. What is it uploading? Oh yeah, cool. Yeah, Distractable had a missing video. But anyhow,
Don't miss out.
where's the button? I don't know where the button is. There it is. I know I'm in the wrong format. I don't care. Let's just keep going.
Juno's discovery left scientists asking whether Jupiter was just an oddball, or if fuzzy cores might actually be a common trait among giant planets. To answer that, the spotlight turned to Saturn. Luckily, we had a spacecraft sitting there at the right time,
Right.
Cassini. Following Juno's 2017 to 2021 results.
Here's the thing. Is this even real? it would seem to not be AI slop, and it says that it's actually fact-based versus mine is hypothesis. So here's the thing, right? Starting with the idea that this could be real, that you have what inside of Jupiter? The idea continues. What if you have the gravity, but then also inside the atmosphere is so big an atmosphere, you still have planets moving through the atmosphere, churning up those weird rings that they have. Because those layers are stirred. Obviously, that can just happen with friction and whatever else. But uh, let's keep going with this guy's video, I guess.
Researchers analyzed existing Cassini data, 2004 to 2017, to test if Saturn shared Jupiter's fuzzy interior, leveraging the mission's comprehensive dataset without needing a new probe. Cassini didn't dive into Saturn the way Juno did for Jupiter, but it had a powerful tool: its ability to read subtle waves in Saturn's rings. Those waves aren't just pretty patterns, they're like seismographs. Inside Saturn, vibrations ripple through the planet, and those ripples show up in the rings as little distortions. By studying them, scientists
Okay.
could probe what Saturn looks like deep inside, much like
Gravitational
how we
waves.
use earthquakes to map Earth's interior. When researchers combined Cassini's ring data with gravitational measurements, a clear picture started to emerge. Saturn II doesn't have a sharp, solid core. Instead, its interior shows the same kind of compositional gradient: heavy elements concentrated toward the middle, but gradually spreading outward without a clean edge. In other words, Saturn also appears to have a fuzzy core. This
Right.
was a turning point. If both Jupiter and Saturn share this trait, it's no longer likely to be the result of some rare random collision. It suggests fuzzy cores are a natural outcome of giant planet formation. Rather than
I
being a
mean,
strange
yeah, but
exception, they might be the rule. And this idea doesn't just stop at our solar
Jupiter is bigger, right? So it could have different rules.
system. We've discovered thousands of exoplanets, many of them gas giants even larger than Jupiter and Saturn.
He's dancing
If
around it. I don't
fuzziness
like that.
is a built-in feature of how these planets grow, then the simple layered models we've been relying on for decades might be far too basic.
Just a
Gas giants may
hypothesis?
not
Okay,
have
fine.
neat separate cores and envelopes, but instead messy, blended interiors that evolve in ways we're only beginning to understand. This changes how we think about more than just structure. It affects how we model a planet's cooling over billions of years, how its chemistry is distributed, even how it might look to telescopes when we measure its atmosphere. In short, Jupiter's fuzziness, echoed by Saturn, forces us to rewrite the rules for giant planets everywhere, from our
Right.
backyard to distant solar systems.
That's not huge. Give me a second. Listen, the fuzzy core issue is not something that is new. It's something that was understood and talked about by other people, such as probably Physics Girl and a bunch of other people that I don't remember the names of at the moment. A lot of people talk about a lot of things. However,
If there's one thing Jupiter is famous for beyond its size and storms, it's its magnetic field. It's the strongest of any planet in the solar system,
right?
stretching so far into space that its magnetotail extends beyond Saturn's orbit, 9 astronomical units from the Sun, influenced by solar-wind interactions. But Juno's measurements showed that
Woo.
this magnetic field isn't the simple, symmetric kind we expected from a planet that spins as fast as Jupiter does. Instead, it's lopsided, with strange patches of intensity and even multiple south poles. On Earth, our magnetic field is generated by the motion of liquid iron in the outer core. It's a clean dynamo effect, where Coriolis forces and rotation organize flows into helical patterns that produce predominant...
Well, that happens with small. When we're dealing with big, it also is affected by... And it's interesting that it's facing away from the star, meaning solar winds kind of push it, you would think. Electromagnetic fields.
dipolar fields. As the conductive liquid moves, it generates electric current.
You see, smaller ones are able to be more confined, they're more reactive. These ones are more loose, a little bit bigger, a little bit more... they'll flow where they may, and are definitely influenced by a freaking star.
Which in turn create a global magnetic field. You'd expect something similar on Jupiter, except the conductor there isn't molten iron, but metallic hydrogen.
Yeah.
Hydrogen that's been squeezed so much by pressure that its electrons are free to move, turning it into a liquid metal.
Also
That
doesn't
metallic
not...
hydrogen, spinning rapidly with the planet, should drive Jupiter's magnetic field in a fairly straightforward way. But Juno's data showed that things aren't straightforward at all.
Right.
Jupiter's field is stronger in
Yeah,
some places,
that weird...
weaker in others, and highly asymmetrical between the northern and southern hemispheres. It also has spots of intense magnetism that don't fit the simple dynamo model.
Yeah.
Scientists had hoped that the discovery of Jupiter's fuzzy core might help explain these quirks. Maybe the...
Okay, so here's what happens when you have a planet smash into another planet. And then it just keeps spinning on its own axis while the rest of your core is doing its own thing. I think Jupiter might have an inside core that's separate and doing its own thing. Yet still fuzzy. How does that make sense?
Diffuse mixing of heavy elements created new kinds of flow patterns that would account for the field's strangeness. The reality turned out to be more complicated. Modeling showed that a stable fuzzy core on its own didn't match the magnetic field Juno observed.
Oh.
In fact, it often produced results that looked even less like Jupiter's actual field.
Right.
That forced scientists to consider other layers and processes. One possibility is helium rain, droplets of helium separating out of hydrogen and sinking deeper, like oil falling through water. This could change the way heat and material move around inside Jupiter, affecting the flows that generate the magnetic field. Another idea is that Jupiter's dynamo doesn't run uniformly across the planet, but instead operates in different regions with varying conductivity and depth.
Or just as a multiple dynamo of, like, let's say you have two different metallic components. One could be of one type of metal, the other of a different, not compatible metal that naturally separates them, but like it's not it's like being a, it's kind of like being is Jupiter tritium? Because it sounds like it just has 3 neutrons doing its own magnetic junk, and a proton, which would explain the bulge. Except it's a fucking planet instead of an atom.
Density. That would naturally create the uneven, patchy magnetic field Juno has mapped. Whatever the cause, the fuzzy core only deepens the mystery. Instead of solving the puzzle of Jupiter's magnetic field, it made it harder to explain. We know metallic hydrogen is a key player, and we know Jupiter's rapid rotation adds energy to the system. But the fine details, why the field is so lopsided, why it has unusual magnetic spots, and why it behaves differently in each hemisphere, remain unanswered. One thing we do know is that this powerful field is directly responsible for Jupiter's incredible auroras.
Also, it
Unlike Earth, where
Also, it completely moves away from Jupiter in the direction away from the sun. So, again, big, lots of flow, not a lot of control. So, yeah, the solar wind's just moving around.
Auroras come and go with solar activity.
We need to apologize to everyone who...
Unlike Earth, where
Healing
auroras
handbook.
come and go with solar activity, Jupiter's are constant, enormous, and hundreds of times more energetic. They're a visible reminder of just how extreme and complicated the planet's interior really
I mean, that storm on the top is the size of multiple Earths. Something, something, I think. Question mark, don't question me.
is.
Don't check my facts. I'm not stating facts. On
Jupiter
that.
and Saturn gave us the first clues,
It's big.
but the real test of this idea is out among the thousands of exoplanets we've discovered. For a long time, when astronomers modeled these distant worlds, they used the same simple assumptions we once applied to Jupiter. A solid, compact core with a clean boundary, wrapped in layers of gas.
No, you use the same core idea that we have for our own planet and any other planet, and you put it on Jupiter, not the other way around.
It made the math easier, and without direct data, no one questioned it too much. But Juno and Cassini forced us to rethink those assumptions. If the two biggest planets in our own backyard don't follow the simple rulebook, then why would planets around other stars? Take
Right.
Jupiter's, for example. These are a class of exoplanets, planets orbiting stars beyond our solar system, that resemble Jupiter in size and gaseous composition, but orbit extraordinarily close to their host stars, resulting in extreme temperatures and rapid orbital periods. They're blasted with radiation, heated from the outside, and their atmospheres are swollen to enormous sizes. For years,
Right.
astronomers struggle to explain why so many of them appear puffier and hotter than expected. If you only imagine them as neat, layered planets, they don't make sense. But if you factor in fuzzy cores, regions where
I mean, Jupiter is considered a failed star, some thought. So, if you consider them like that, then of course they're going to be puffy.
heavy elements are blended gradually with lighter ones, suddenly the pieces fit better. Those gradients slow down cooling and change how the interior evolves, helping to explain why these planets stay inflated. This doesn't mean every exoplanet has a fuzzy core, but it tells us we need to be careful. We can't assume that what's inside is simple just because it's easier to calculate. In fact, fuzziness might be the default outcome of planet formation. Instead of clean structures, gas giants across the galaxy.
Look, you're not going to get fuzziness out of just anything. It happens a lot more when you have more stuff and depending on the composition. If you have whatever else and tons of metal was able to get in there that you are able to have a metal core like you have with Mars and Earth, then yeah, you're going to end up with a solid planet and whatever else. And also, it's covered with a bunch of rock, not just metal. So maybe Jupiter is just the one that doesn't have a lot of rock. There is a big space debris belt, though.
May be full
Full
of
of rocks.
gradients, partial mixing, and blurry boundaries. That changes not just how we picture them today, but also how they might change over billions of years. The challenge, of course, is that we can't send a probe to every exoplanet. The best we can do is observe their atmospheres with telescopes like JWST, measure their mass and radius, and build models to fill in the gaps. Those models are only as good as the assumptions we feed into them. And now, thanks to Jupiter and Saturn, we know our old assumptions were too simple. The next generation of models will have to treat fuzziness as part of the equation. Future missions in our own solar
I'm
system.
going to have to repeat. This video has a picture of a fucking black hole as its thumbnail, probably because they thought I would be tricked into thinking that we're going to learn that it has a black hole in it.
System will also play a big role.
I'm
Although
not
Juno's
hearing black
extended
hole.
mission concluded in late September 2025, after relaying its final data before plunging into Jupiter's atmosphere, the wealth of information it returned continues to shape new discoveries. Saturn could be the target of new missions in the decades to come. Every bit of information we gather about how these giants behave up close gives us a better chance of understanding the ones we see light years away. Even with Juno's discoveries, much about Jupiter remains unresolved. We don't know if the fuzzy core...
Oh, for fuck's sakes. I think this is bait. I hate this. I hate it. Fuck. No, I hate that thumbnail because that's what I was... Oh, they didn't know, saw coming. There are older videos about this. We already know fuzzy core. Failed star. Whatever. I'm leaving. I'm taking my children. And I am not coming back. I was promised sushi. And all they had was soup and clothing for some reason. All fairness, did he say anything that was actually wrong? Honey, the thing is, this has already been said. It's my hypothesis, which is actually based off something real, is like I'm analyzing it, I'm actually constructing a theory. Well, you got a couple of them. What if you have planetoid type stuff inside Jupiter, which causes the stirring? Or what if you have, but it seems to be a fuzzy core. Well, what if you have a central core that's made of one type of metal and a different core of a different type of metal? Could be neodymium, could be a different type, whatever, some other type. And those magnetic fields run differently because they are different substances on doing different regular things. So, like, one of them could be liquid mercury or whatever, while the other one is liquid helium, and they don't quite mix. So, you got like one planet of one substance, which is still not solid, and another planet of another substance, which is still not solid, and you got your multi-magnetism stuff. It still doesn't explain how the magnetism is flowing backward away from the star, or does every magnetic field work like that and not be specific like we say it is? Because what if our own magnetic field isn't a beautiful toroid? Like, you gotta think, like, I think that with a smaller planet, and it makes sense, it has tighter grip on its magnetic field, so the dynamo or whatever else is working, it's more solid, it's more controlled, and it can't go out of position as much. But then you see a freaking star, and the star has magnetic stuff going crazy all over the place. So it makes sense that Jupiter is also kind of protostar, kind of doing same star behaviors. This is not new science or information. But the video felt sensationalism. It felt like it added nothing. At least I had some ideas to put in, like talking about electrons. The reason I talk about atoms and stuff is because the orbital radius of atoms and their electrons is similar to the idea of, just scale it up, you got a planet, and the orbits of everything along with. The difference is you don't have planets going around quadrillions of times per second. That doesn't happen. That's what electrons do. Look it up or do the math. If you don't believe me about electrons going that fast, I'll do some quick maths for you, right? Because I can. Starting with 2.2 kilometers per second, or 2.2 thousand kilometers per second, otherwise known as 2.2 million meters per second, is the speed of an electron. Compress that to the orbit of an atom, and it's going around about a couple quadrillion times. Because the order of magnitude of the size around an atom, or its orbit around an atom, and the distance it's capable of going in a second, equals about 2.2 quadrillion orbits per second, or atomic widths per second. It's about 5 trillion orbits per second, or something. The numbers are massive. So the fact is, this is why electrons look like a blur. They look like a blur because that one electron went around so many times in a second, it freaking looks like a blur to our scanners, no matter how good they are. So persistence of vision, it's like this, but it's just one, and it looks like a blur. And it's like, that's crazy, and that's how it is, because it's so fast and such a tiny space. That's what electrons do. So, yeah. Compared to atoms, planets don't have nearly as much attractive force for size. However, if you think about what happens with protons and neutrons and electrons with their attractive forces, you can do some calculations and realize that that relationship of matter to other localized matter is kind of like what happens with gravity. It might be exactly what's happening with gravity, which is why Jupiter is connected to the sun directly. Whatever. This was a waste of time. Don't look up the video. I think it's spoof. And do watch this video because you can actually watch it. It's here.
This episode is strapped. You okay? All right. It's very polite. Not 3 minutes in finishing. I went to no, I can keep that up for hours. Per walking comes out. Dipping, you're like, oh my god. Trouble, great. He wasn't good. Mark. Out of you.
The video exists. Hooray! Go watch it now. Do it. Screw me. Watch this.